Hello everybody. Today's lesson will be covering on chapter 5.5 on graphs and applications of logarithmic functions. The objective of today's lesson is to sketch graphs of logarithmic functions and also to use logarithmic functions on models. That will mean that we are going to be looking at problem sums that require the use of logarithmic functions.
Let us first take a look at the graphs of logarithmic functions where the generic equation of these graphs are going to be y equals to log x base a. So what's going to differ, how the shapes are going to differ is dependent on the value of a itself, whereby this is when a is more than 1, and on the right we have the case where a is between 0 and 1. Okay, firstly I want to bring to your attention that for both cases the x-intercept will actually be equals to 1. The reason is because to find the x-intercept, that means that y is equals to 0. So when y is equals to 0, right, that will only happen when a to power 0 is equals to x, when I translate this logarithmic form into the index form. Okay, so the x value will be none other than 1, because a to the power of 0, or rather any value of a when power of 0, it will be equals to 1. That is the reason why the x-intercept for both cases will be equals to 1. Alright, the next thing that I want to bring to your attention is to observe that for both graphs, they are appearing on the positive x-axis portion. So that means that the graph doesn't go into the negative x-axis part. So positive x only. Okay, the reason for this is because in our logarithmic equation, right? So if I were to erase all this, so in the logarithmic equation, we understand that a logarithm can only be defined when this value for x over here has to be more than 0. Okay, so always more than 0 in order to be defined. Okay, so that's why our graph will always appear on the right hand side of the y-axis, or in other words, it is also in the positive x-axis side. Let us now take a closer look at the left side where a is more than 1. We see that the graph shape is going to be of this manner, whereby y increases as x actually increases. Okay, so that is the shape that we need to take note of when a is more than 1. What this means is that, for example, your equation for the logarithmic function can be things like y equals to log base 2, okay, log x base 2, or maybe y equals to log x base 3. All right, it need not always be integer, all right, or positive numbers. It can be log 2.5 base, right? So, or rather log x base 2.5, or even y equals to log, maybe in a fraction, okay, we can have 3 and 2 over 7x, although this is extremely rare. All right, but in general, okay, regardless of what a value is, as long as it is more than 1, the graph shape will always be in such a manner. Okay, I want you to take note that at this section over here, x actually approaches 0 as y becomes increasingly negative. So it is approaching but never touching. All right, so never touching the y-axis. Okay, so this is somewhat a similar concept to when we were talking about the exponential functions. Now moving on over to the right side, okay, where we have we have a to be between 0 and 1, right? Okay, that will mean that, for example, you can have equations that are like y equals to log x base 0.2, for example, or maybe y equals to log base half, right? Log x base half. Okay, so these are some examples of how a logarithmic function could be that will give you this shape over here. Okay, so with this shape, it means that y actually decreases as x increases. Okay, and I also want you to take note that over here, x actually approaches 0 as y becomes very large, meaning to say that it is approaching the y-axis but never ever touching it. So similar idea to your exponential function as well. On this slide here, I am presenting to you the comparison of the graphs of logarithmic and exponential functions. I will not talk a lot about this slide. Okay, it is just a general overview for us to see the differences between logarithmic and exponential functions clearly. Okay, but what I really want to talk about is what if, okay, in this particular case, when a is more than 1, right, how does the logarithmic function and the exponential function actually relate to one another? Likewise, if I look at the other case where a is between 0 and 1, how does the graph actually relate to each other? So how's this relationship between log and exponential function going to be like? So moving on to the next slide, we have over here the graphical relationship. Okay, so I was talking about when a is more than 1. Okay, so when a is more than 1, my logarithmic function will be of this pattern, the blue one here. And then after that, for the exponential function, it is this one over here. Okay, so for example, if I were to compare y equals to log base 2x and y equals to 2 to the power of x, okay, the graphs will actually look like this. So what we see is that if I have this line y equals to x going on, okay, if I plot out this line over here, they are actually mirror images of each other. So the exponential graph and the logarithmic graph, they are actually mirror images. They reflect in each other. So imagine putting a mirror along y equals to x, you will see that it is a perfect reflection. Okay, so likewise, although it is not very obvious, okay, when we see when between 0 and 1, okay, so if I were to have y equals to maybe half x, half to the power of x, and y equals to log half, log x base half, right? Okay, so the blue one versus the green one, they are actually supposed to be reflections of each other as well. So if you were to look carefully, okay, this part here actually reflects in over here, and then after that this section here actually reflects with this section here, right? So between logarithmic and exponential functions, right, they are always reflections of each other in the line y equals to x, provided that the a value, the base value, is actually the same. Okay, so we cannot say that they are reflections if I had maybe y equals to log base 3x over here, and then over here I have y equals to 2 to the power of x. So they cannot be reflections. So the a value needs to be the same, right? Let's first take a look at try 25, okay, where we want to do some sketching of the following graphs. So in part A, we have y equals to log x base 1/3. So because the base itself is 1/3, that means that it is the case between 0 and 1. So therefore, the graph shape will actually appear in such a manner, and then the x-intercept will be at 1. So we observe here that it is approaching the y-axis but never touching it. Then in part B, we see that the base itself is actually 5, and that is the case whereby a is more than 1. So the shape will actually be in such a manner. Then after that, the x-intercept will be at 1. And then we observe over here that it is actually approaching the y-axis but never touching it. We will now take a look at try 26, okay, whereby we are going to touch upon the applications of logarithmic functions. So that means that we're going to be looking at some problem sums that involves logarithm itself. Okay, so it is somewhat similar to how we did problem sums in exponential functions, just that now we're doing something involving logarithm instead. Okay, so let's look at this chemistry context, whereby we are given pH, whereby pH is a measure for the acidity of a solution. So maybe some of you are already familiar with that in your chemistry lessons. Then the pH value is being given by a particular formula, which is pH equals to negative log base 10, and then after there's this square brackets and then H plus. All right, this square brackets with this H plus, right, okay, is actually just some symbol to represent the hydrogen ion concentration. Okay, you will study more about that in your chemistry further on in the year, or maybe some of you have already covered it. I'm not too sure about that. But anyway, looking at part I, right, the question says that the pH of a human blood is normally 7.4. What is the hydrogen ion concentration? So the question is actually asking you to find, all right, the value for this H plus. Okay, so don't forget it is just a symbol. So the bracket comes with the symbol itself, right? Please don't change it into a round bracket. Okay, that is not correct in the chemistry sense lah, right? So give your answer in scientific notation. Okay, that means that it will be in mole per liter lah. Okay, that's the unit for this concentration. Okay, so you can ignore all the chemistry terminologies if you're not familiar with it. We just need to focus in identifying what is the symbol to be using. So the pH is 7.4. So when pH equals to 7.4, okay, we substitute 7.4 into the formula given, all right, and then we will be having this. We are trying to find out the hydrogen ion concentration. That means a square bracket H plus, right? That will mean that if I were to shift the negative over to the left first, I will have negative 7.4 log base 10 H plus. Okay, then I change this logarithmic form into a index form. So I will get 10 to the power negative 7.4 equals to H plus. Okay, then now I can press into my calculator to find out what is that value. So the concentration is actually about, okay, let me write it on the right instead. The concentration is about 3.9810 times 10 to the power negative 8. Okay, that's truncated 5SF, always leaving our answer to be in 3SF, so that will be 3.98 times 10 to the power negative 8. So we're leaving our answer in standard form. Okay, then take note that we will not accept this answer because this answer over here is not meaningful. What do I mean by that? Because 10 to the power negative 7.4, I wouldn't know what is the exact value. Are they in 10 point something, or it's not even a standard notation also, standard form as well. So therefore it is not meaningful, because when we evaluate this, we see that it is actually 3.98 something. Okay, that is a more meaningful number to discuss. All right, so that is how we find the value for part I. Okay, now going into part 2, we have a solution with pH less than 7, okay, that will be called an acid, and a solution with pH greater than 7 is called a base. So these are information itself that will tell us when is it called an acid, when is it called a base. Okay, so black coffee has a hydrogen ion concentration of 5.1 times 10 to the power negative 5 mole per liter. So this means that this H plus, that value is 5.1 times 10 to the power negative 5. So that is what it means. Then we are trying to find out what is the pH level of the black coffee, and subsequently determine whether this black coffee is it an acid or a base, and that will be determined by the information provided in the first sentence. So using the formula again, pH is equals to negative log base 10, okay, and then the hydrogen ion concentration, which is 5.1 times 10 to the power negative 5. Okay, instead of writing log base 10, right, you may also want to choose to write the common log. That is also fine. Okay, it means the same thing. All right, so to press this into the calculator, all right, I hope that you are familiar with pressing this into calculator. We would get about 4.2924 in truncated 5SF, and that would be 4.29, the 3SF value. Okay, so now that we see that the pH value is 4.29, that is actually less than 7. So therefore, we can say that the black coffee is actually an acid solution. All right. Moving on to part 3. If black coffee in part 2 is diluted by a factor of 15, how would its pH be affected? Okay, so when we say that it is being diluted by a factor of 15, right, what this means is that the hydrogen concentration level, okay, is being divided by a factor of 15. Okay, so because the hydrogen concentration level originally is 5.1 times 10 to the power negative 5, so in this question, the H plus value will actually be 5.1 times 10 to the power negative 5 divided by 15. So that is what it means. Then after that, now that we want to find out the pH itself, it will actually be negative log base 10 with the new hydrogen ion concentration. Okay, so the value when we press in the calculator will be 5.4685. 3SF will be 5.47. Okay, so how this pH is actually being affected is that we can draw a comparison by taking a difference in it. Okay, so writing it on the right, so therefore the pH would increase by 5.4685 minus away 4.2924. That's the answer in part 2, which is about 1.1761, and 3SF will be 1.18. Okay, so it will increase by 1.18 in value. Oops, sorry. So that means that it is actually becoming more of a base solution instead of being acidic anymore. We'll now move on to try 27, where we're going to look at a similar question. Okay, just that it's no longer about pH. Alright, so in this question, we are given that a cup of coffee is left to cool on the table, so the temperature will drop. Okay, so it's temperature T degrees Celsius, T minutes later. So there are two different types of T over here. One is capital letter T to represent the temperature, and the other one is a small letter t to represent the time. And the formula that we are going to use is this one over here. Okay, so in part I, we want to find the temperature 5 minutes later. That would mean that since the units are the same, okay, so our small t is equals to 5. Okay, so substituting that into the equation itself, or rather the formula itself, we will have this, and you just have to key into your calculator, and we will get the final answer to be 65.2. So the temperature 5 minutes later will be 65.2 degrees Celsius, 3 SF. Alright, so that's for part I. Now in part 2, we want to find the time when its temperature is 50 degrees Celsius. So that means that the capital letter T is going to be 50. So when capital letter T is 50, upon substitution, we are going to get this. Okay, and clearly over here, the manipulation doesn't seem to be very intuitive. Okay, but we already have the skills to actually solve this question. So let us first shift over 27 to the left. So that means to minus 27. And then that means that it would be equals to 23. So 58 times 0.92 to the power of t is equals to 23. Hence 0.92 to the power of t is equals to 23 over 58. Okay, so at this juncture here, how do we go about finding out the value of t? We will use our logarithm concept. Don't forget, we are looking at the logarithmic chapter over here. So we will apply logarithm on both sides of the equation. So this is one way that we can do things. I'll explain another way later on. Oops, sorry, not 0.92. 23 over 58. Okay, then I can bring down the t by my logarithm law. And then t will be equals to log 23 over 58 divided by log 0.92. So keying this entire thing into the calculator, we will achieve 11.092 or 11.1 minute to 3 SF. Okay, so that means the time taken, right, pardon me for not having enough space, we will have time taken to be 11.1 minutes. Right? So this is one way whereby we apply logarithm on both sides. Okay, so you notice that I took the common log. Okay, so you can use any kind of logarithm base. So you want to use base 2 also fine, right? Just that your calculation later on will be slightly more complicated. Okay, so we want to make use of our calculator at the end. Okay, where at this step we use calculator. So that's why we will choose to have common log, which is the one that has base 10, or you can use ln also fine. Okay, so that means your natural log. So natural log. Okay, that's a wiser choice. So usually if it doesn't involve exponential function, right? Okay, that means the letter e, the value of e, I will avoid using natural log. So I will usually go ahead with the common logarithm, which is the one with base 10. Okay, so this is one way of doing things. Another way, okay, if I were to draw in comparison and write it in green over here, is that now that I have 0.92 to the power of t equals to 23 over 58, right? Okay, I am familiar with doing index form into logarithm form. So that means that it will be log 0.92 as the base, then 23 over 58 equals to t. Okay, so then now how do we key this value, okay, this logarithm value into the calculator? Okay, we know that already, whereby we can change the base to base 10. So it will be log 23 over 58 base 10 divided by log base 10, 0.92. Okay, so you find that this calculation here, all right, it is actually the same as this one here. Okay, so they are the same kind of calculation. So either way is fine. So the one on the left is to actually convert index form into log form. Right, so that's how we actually go about solving part 2. Okay, moving on to part 3. We want to show that t is equals to log 0.92 base. Okay, or rather, let me correct myself. It will be log bracket t minus 27 over 58 with base of 0.92. Okay, so we want to achieve this, and the only way that we can achieve this is to make use of what we were given earlier, which is this formula. Okay, essentially what you need to do is to make the small t as the subject. So we apply similar manipulation methods as per what we were doing in part 2. Okay, so in part 2 we apply logarithms on both sides or to do the conversion, okay, from index to log form. So now let's go about doing that. Okay, we will shift the 27 to the left and we achieve this. Then we divided by 58, right? Then after that, now it is an index form. Okay, we need to change it into our logarithm form. Okay, so this is 0.92 to the power of t. Maybe let me write it clearer. Okay, so I'm going to have log base of 0.92, right? T minus 27 over 58 equals to small letter t. So here you go. We have shown what we are expected to do. Okay, so shown. So that's it for part 3. We will now take a look at exercise 5.5 question 6, where the question talks about radioactivity. So we are told that there is 100 grams of radium at the beginning that is stored in a container. Then after that, the amount of radium after t years, okay, is actually given by this formula over here. So in part I, we want to find out how much of the radium would remain after 10,000 years. Okay, so that will mean that when t is equals to 10,000, we will substitute it into the formula itself. and hence we would be having this. Okay, then after that, keying that into the calculator, we will achieve the truncated 5SF value to be 1.3856, which then gives us 1.39 in 3SF. Okay, so then after that, this means that the radium, the amount of radium after 10,000 years will be 1.39 grams. All right, moving on to part 2. The question asks, how long will it take before the amount of radium is being halved? So at the beginning of the question, it says that there is 100 grams of radium. This would mean that the amount that we are thinking about now would be half of that amount, okay, half of 100 grams. So when R is equals to half of 100, that will be equals to 50. So substituting that into the given equation, we would arrive at this. Do notice the number of zeros carefully and don't miss out on any one of it. Otherwise, it will change the value. Okay, so upon arriving at this equation, right, how are we supposed to go about solving this equation? We will first take this 100 and shift it over to the left side. That means we divide it over to the left. 50 divided by 100 will be equals to e to the power of negative 0.0004279 t. Okay, then now the t is in the power. So what are we supposed to do with it? We need to actually make use of our logarithms. Okay, so what we can do is to apply logarithm on both sides of the equation. And we will arrive at this. So when we apply logarithm, okay, in this case, I chose the natural log. The reason is because the base that we're seeing over here is an exponential value. So that's why it will be more natural, okay, to choose the natural log. All right. So you can of course choose the common log. There's nothing wrong with that. Just that when you use the natural log, right? Okay, the ln e to the power of all these numbers over here will allow us to actually bring this power down first using our power law, and we see that we will get the number times ln e, and ln e is none other than just the value of 1. All right, so therefore we easily so-called got rid of the exponential value itself. Okay, then to find out the value of t, we will just take ln half, okay, divide by negative 0.0004279, right? Do take note of how the brackets are being formed. This ln half is standing on its own, divide by the negative value. Okay, keying that into the calculator. Okay, of course, in this case, you can write it into a fraction form, not an issue. Just make sure you have enough space when you're writing and don't cramp up your handwriting. And then we will have 1619.88. Okay, and then finally, we need to round this off to 3SF, so we will get 1620. Okay, so the number of years that it will take, okay, to actually halve the amount of the radium would be 1620 years. So number of years would be 1620. Okay, and that's it for question 6. We will now take a look at question 13, which talks about health. Okay, and this question, the context itself is actually very close to what we are facing right now with the coronavirus. So let's take a closer look with this question first. Okay, it says that in a school with 1,500 students, one student returned from vacation with a contagious flu virus. Okay, so there are 1,500 students in the school. The spread of the virus through the student body follows this equation over here, where y, okay, is the total number of students infected after t number of days. So the school would cancel classes if 40% or more of the students are ill. So I've already highlighted all the crucial information given in this question. In part I, we want to find out how many students will be infected after 6 days. So after 6 days, that means t is equals to 6. We will substitute that into the given formula. And then we could key this entire thing into the calculator and arrive at the truncated 5SF value of 147.94, which round off to be 14823 SF. Okay, so the number of students infected would be 148. All right, moving on to part 2. You want to find out after how many days would the school cancel classes. So the question says that the school will cancel class if the number of students being infected is actually more than 40%. Okay, so the question says that y is the total number of students infected. So if you were to translate that into a mathematical statement, okay, so it will mean that school would cancel classes if y itself, the number of students, or rather the number of students infected is more than or equals to 40%. So that's 40 over 100 times the total number of students in the school, which is 1,500. So with a simple calculation, we will see that it means y is more than or equals to 600. Okay, so because we're trying to find out the number of days, okay, after how many days would the school actually cancel class, we are going to find out, okay, how many days will it take? How many days, sorry, will it take to have 600 infected students? That will mean that y is equals to 600. Okay, so we will take this process into answering this question. So when y is equals to 600, we will substitute this into the given formula, okay, and we will arrive at 1 plus 1499 e to the power of negative 0.85 t 1500 then equals to 600. So we arrive at this equation. Then we will do some cross multiplication to get rid of the denominator. So our aim here is to try to find out the value of t. Okay, so you will do some quick manipulation here. This will give us 5 over 2 minus 1 equals to 1499 e or negative 0.85 t. So this is 3 over 2. Okay, we can divide it by 1499. Alright, then now we can take ln on both sides. Okay, so 3 over 2 when divided by 1499, that will give us 3 over 2998. And as mentioned, we will take ln on both sides. Okay, you can put brackets over here. The meaning will still be the same, right? And that will actually get rid of the exponential value, and this will be negative 0.85 t. Okay, so therefore t itself would be none other than taking ln 3 over 2998 divided by negative 0.85. Okay, and putting this into the calculator, we would get 8.1259. So the 3SF value will be 8.13. But then the thing is that t is about the number of days, right? The question isn't exactly asking the number of days isn't very meaningful to talk about 8.13 number of days. So in this case, okay, we will understand that about eight days thereabout, okay, would be when the number of students being infected will be about 600. Okay, but I want you to be very careful, because if I were to talk about 8 days, okay, at t equals to 8, that means 8 days, right? The number of students being infected would actually be lesser than 600, because only at 8.12 then there are 600 infected students. Okay, so that means that in order to have more than 600 students being infected, okay, the final answer that we should choose is that, okay, it will be 9 days. So the school should cancel classes after 9 days, right? So we should be choosing 9 days and not 8 days. So we need to be very careful in the way we so-called do a rounding or making a decision over here, because in this case we are not trying to do a rounding off, we are trying to make a decision according to the context of the question. All right, I hope you're understanding what I'm trying to say. Okay, so that's it for this question. And that's the end of today's lesson. I hope that you're able to meet the two objectives for today's lesson, which is to learn how to sketch the graphs of logarithmic functions, and also to learn how to use logarithms to solve problems, okay, that are related to real life. All right. If you have any questions, please do drop by the Google Meet. All right. Otherwise, please complete the homework, and I'll see you again in school. Bye bye, everyone.